let us start with some conditions, right. So, our active subsystem requires nominal value of 1.8 volt, can tolerate a max of 2.1 volt and a min of 1.2 volt, consumes 100 milliamp of current. Evaluate a resistive divider for its suitability as a power source, right. This is what we are going to try and do now. So, let us say that okay, I have okay, one thing I forgot to mention, we will add here. Input source is a lithium ion battery that can go from 3 volt to 4.2 volt. So, 3 volt is V in min, 4.2 volt is V in max. Okay. So, these are the conditions we have to work with. So, let us say we say okay, this is we have V in, and all we are going to do is do a simple resistive divider to generate V out, right. So, now this is our circuit, we are going to calculate R1, R2 and all that in a second. But before that, let us start with first thing of interest is the input voltage range. So, let us say this is the okay. So, input voltage range is very simple. V in min is 3 volt, V in max is 4.2 volt, that is already provided in the statement here itself. So, that takes care of the input voltage range. The next parameter of interest is the typical output voltage. So, now so what we know is that so typical output what we know is that, let me just complete this in all these pictures, then go back here. All right. So, what we know is that the active subsystem can tolerate a maximum of 2.1 volt, right. So, if you go back here, we say that the active subsystem can tolerate a maximum of 2.1 volt. So, what we have to do is say that okay, when the battery is or when the input voltage is 4.2, the output should be 2.1. So, what this essentially means is that when V in equal to 4.2 volt, V out should be less than or equal to 2.1 volt. We have to now choose it. So, what we will do is to maximize, we will say let it be equal to 2.1. So, we have as a result R2 divided by R1 plus R2 into 4.2 equal to 2.1. This is this is V in, this is V out, right. So, you have R2 by R1 plus R2 is 2.1 by 4.2, which is half. So, R1 equal to R2, right. So, now if R1 equal to R2, let me just minimize this and get it here. So, now if R1 equal to R2, what should R1 and R2 be? We have to be able to provide a reasonable amount of current. So, what we will do is again we will start with some values and then we will play with it and see if the values we have are reasonable or not. So, I am going to postulate that let R1 equal to R2 equal to 5 ohms. So, let us start with this number and let us see where it leaves us. Okay. So, R1 is equal to R2 equal to 5 ohms is what I am going to assume. So, now let us with that background. So, now that we have the circuit, so this is 5 ohms, this is also 5 ohms. Let us calculate the typical output voltage. Typical input voltage for the battery is 3.6 volts. Lithium ion batteries, while they vary from 3 volt to 4.2 volt, they spend a lot of their time at 3.6 volts. As you are discharging the battery, a large fraction of that discharge time is centered around a battery voltage of 3.6 volt. So, we will call that the nominal or typical input voltage. So, V out typical is 0.5 times V in typical. So, this is 0.5 into into 3.6, which is 1.8 volt. So, V out typical is 1.8 volt, right. So, that is the second thing we had to calculate. What is the third thing we had to calculate? We had to calculate the output voltage range. So, now let us go back here, let us see if this will, very nice. Just going to minimize this a little bit. So, we know that this is 5 ohms, we know that this is 5 ohms. Now, we are interested in the output voltage range. So, here we know that V out is equal to R2 by R1 plus R2 into V in. So, this is just 0.5 times V in. So, when V in is high, V out will be high, when V in is low, V out will be low. So, the output voltage range in this case at least is pretty much set by the input voltage range, right. And again I want to draw the distinction between somebody who is building a power regulator and somebody who is using a power regulator. At this point we are users of the power regulator, we are only trying to figure out okay somebody gave me a power regulator, is it suitable for my requirement or not, that is it, right. Somebody who is designing might not even look at the resistive divider, we are looking at it in the context of okay we want to keep our cost low. So, let us start with the most basic system and see whether it will work for us, right. So, V out is 0.5 V in, which means that V out max is 2.1 volt, is just 0.5 into 4.2 volt, and V out min is 0.5 into 3 volt, it is 1.5 volt. So, the V out range is just 1.5 volt to 2.1 volt. This is V out range. Okay. Let us look at the next parameter. If this all looks too basic, just bear with me, it will get a little more interesting in a second. So, now we have output voltage So, now things are going to get a little more interesting. Let me just So, now you look at what is output voltage accuracy. So, we know that V out is equal to R 2 divided by R 1 plus R 2 into V in. Let us, when we talk about, we already talked about the output voltage range, which is the variation you get in the output voltage when the input voltage is changing, right. Accuracy is a slightly different thing. The question around accuracy comes from, let us say that the input voltage is not changing. The resistors are, like I said, physical components that are produced using a certain manufacturing process, which means that they will have both, they will have unit to unit variation, they will have a lot to lot variation, and these are captured in the form of a certain type of distribution in its in the resistors parameters. Now, if the resistor value has, let us say, a normal distribution, then you wonder, okay, how will the accuracy of the output voltage be? So, as the resistor varies, as let us say I built 1000 such resistive dividers. When I build 1000 resistive dividers, what is the, and I apply 3.6, I know that my typical output value is 1.8 volt. If I apply 3.6 volt to each of these 1000 voltage dividers, will I always get 1.8 volt? Now, because the resistor value is varying, you will not always get 1.8 volt, you will get a spread around 1.8 volt. It will still be centered at 1.8 volt, but you will get a spread around 1.8 volt. Output voltage accuracy is a measure of that spread. That is important because again, I told you that this block can take between 1.2 and 2.1 volt, it is a very wide range. You ideally want to give it as kind a voltage as possible or operate that subsystem in its sweet spot. Now, any variation means that over time or over from a unit to unit on a unit to unit basis, the supply being offered to that subsystem will change, which means that I do not get the same performance from unit to unit, right. So, what we will do now is attempt to calculate how this accuracy will look as a function of the accuracy in the resistance values. So, what we are looking to do is estimate delta V out by V out as a function of delta R1 by R1 and delta R2 by R2, right. So, delta R1 by R1 you can think of is the relative variation of resistance R1, delta R2 by R2 is the relative variation of resistance R2. Now, we are interested in understanding, okay, how is delta V out by V out related to delta R1 by R1 and delta R2 by R2. Now, if these resistors have a normal distribution, again you've probably done, I think you've done a statistics class either in the first or second semester. So you would be familiar with terms like mean, standard deviation, etc. What we are going to assume is that we are looking at units that have a normal distribution. So we will be measuring the variation or the variability in terms of variance and the square root of variance, which is standard deviation, and we will see how the standard deviation of delta V out by V out will depend on the standard deviation of delta R1 by R1 and delta R2 by R2. So that gives us an estimate of okay, if the resistor is, let us say, 1% accurate, to what degree will the output voltage be accurate, right? That is what we are going to try and estimate now. So when we are, I opened a new page so that it's easier for us to look at the working. So again, what we are interested in is the extent to which the output voltage changes when the component values change. So let's say that we have two components here. Let's say R1 goes to R1 plus delta R1 and R2 goes to R2 plus delta R2. We are interested in figuring out what happens to V out. Let's say it goes to V out plus delta V out. We are interested in deriving delta V out as a function of R1, R2, delta R1, delta R2. So what do we know? We know V out is equal to R2 by R1 plus R2 into V in. And V out plus delta V out, it's the same resistive divider formula, is R2 plus delta R2 divided by R1 plus delta R1 plus R2 plus delta R2 into V in, right. So now delta V out, I have just moved V out to the other side, it is R2 plus delta R2 by R1 plus delta R1 plus R2 plus delta R2 into V in minus V out, right. I have just moved the V out to the other side, but we know that this V out itself is R2 by R1 plus R2 into V in, correct. So what we are going to do is let me just so let's do a new page. Minus R2 by R1 plus R2 into V in, right. So this is V out, we have just replaced V out by R2 by R1 plus R2 into V in. So let's sort of take R1 plus R2 out as a common denominator. Let's pull V in also out. Now what you will get is R2 plus delta R2 into R1 plus R2 minus R2 into R1 plus delta R1 plus R2 plus delta R2 by R1 plus delta R1 plus R2 plus delta R2, right. Just taken common denominator. Let's expand the terms. You get V in by R1 plus R2 into R2 R1 plus R2 square plus R1 into delta R2 plus R2 into delta R2. This is the expansion of the first set of terms minus R1 R2 minus R2 into delta R1 minus R2 square minus R2 into delta R2. This is the expansion of the second set of terms divided by R1 plus delta R1 plus R2 plus delta R2, right. Now, let us do some cancellations. We have R2, R1, we have minus R2, R1, right. So, that we can cancel. We have R2 square, we have minus R2 square, that we can cancel. Then we have what else do we have? We have minus R2 delta R2, we have plus R2 delta R2. So, that also we can cancel, right. So, once we eliminate these 6 terms, what are we left with? We are left with, so all of this is delta V out, right. So, we are left with delta V out is V in by R1 plus R2 into R1 delta R2 minus R2 delta R1 divided by R1 plus delta R1 plus R2 plus delta R2. Okay. So, let us do a little bit of optimization before we draw conclusions. So, I am just going to go to a new page. So, let us start from here. What I am going to do is, and it will be obvious why in a minute, I am going to multiply numerator and denominator by R2 here. So, this is V in into R2 by R1 plus R2. Now, I multiplied numerator by R2. So, ideally I should divide by R2 somewhere. So, we will make this delta R2 into R1 by R2 minus delta R1. So, both these terms in the numerator I have divided by R2, divided by R1 plus delta R1 plus R2 plus delta R2, right. Now, here we can say that delta R1 is much less than R1, delta R2 is much less than R2, because we are talking about component variations that are a small fraction of the value of the component itself. So, it is not like delta R2 is going to be 50% of R2, maybe it is 1%, maybe it is 2%, still very, very small numbers. So, what we can do is, because of this we can say that R1 plus delta R1 is approximately equal to R1, R2 plus delta R2 is approximately equal to R2, right. We will make that first assumption. And what is V in into, what is this? This is V out, right. So, we will say delta V out is now V out into R1 by R2 into delta R2 minus delta R1 divided by R1 plus R2, right. So, we have, I am just going to center the final result here. So, we have delta V out by V out is R1 by R2 into delta R2 minus delta R1 divided by R1 plus R2. Okay. So, this is the result we have arrived at, and it gives us the relationship between the fractional change in output voltage as a function of the component values and the fractional change in the component values, right. So, again let us go to a new page and start with this. Now, it is important to, oh, I missed something. So, this is R2. So, it is important to sort of recognize that the variation in R1, which is delta R1, is completely uncorrelated with the variation in R2, which is delta R2. What does that mean? Again, I think you've taken a statistics class, so you probably know what correlation means. If two variables are uncorrelated, it means that when you do sigma of R1 R2 or sigma of delta R1 delta R2, if they are uncorrelated, sigma of delta R1 delta R2 will go to 0 because they both vary in random directions. The sum of their product will go to 0. So now this is a function that shows the fractional dependence. We are interested in calculating the standard deviation. Standard deviation is square root of variance, and variance is the sum of the squares of the term. So the variance square of delta V out or the variance of let me just erase this a bit. So maybe what I will do is I will let me keep so we have delta V out equal to V out nominal into R1 by R2 into delta R2 minus delta R1 by R1 plus R2. So the variance of V out, which is the sum of the squares, will be V out square into R1 by R2 square into the variance of R2 plus the variance of R1 divided by R1 plus R2 the whole square. Now you are familiar that a minus b the whole square is a square minus 2ab plus b square, and sigma of a minus b the whole square is sigma a square minus sigma of 2ab plus sigma of b square. If a and b are uncorrelated, sigma of ab goes to 0, which is why when we calculate variance of uncorrelated items, you say that the variance is just the variance of the first term plus the variance of the second term. The cross product or the sum of the cross product will go to 0, right. So standard deviation, which is the square root of variance, will be V out divided by R1 plus R2. We can put that denominator wherever we want into, I wanted space for the square root, so I moved R1 plus R2 out, into square root of R1 by R2 the whole square into the variance of R2 plus the variance of R1. I have just taken square root on both sides, right. So this is our key result, which now tells us the relationship between the variance of the resistors or the variance of the components themselves and the variance of the output voltage. Now, I have derived something. Obviously we have to validate that what I have derived is correct, and this is an exercise that I would encourage you guys to do, where what you can do is you can say, and you can do this with any tool, right. Sometimes we think, oh, I have to do statistical analysis, I need a complicated tool to do statistical analysis. You actually don't. Most statistical analysis is just really working with random distribution in our case. So as long as you have a way to generate an array that is a normal distribution, you can do this with just about any tool, right. So what I would encourage you to do is to generate an array for R1, generate an array for R2 that are based on the normal distribution, and then see what delta V out looks like or V out looks like, and look at the variance or standard deviation of V out and see whether it is consistent with this formula, right. I am going to ask you to do it. What I have tried to do is put something together with Excel. Now this is something I have built to validate that whatever formula I have come up with is correct. I would encourage you to build your own. I will also see if this can be made available to you, so you have some starting point, but I'd really encourage you to build this up on your own, right? So what have I put together here? The rows 1 to 3 are essentially the inputs. In my case, I have started with, okay, let the average value of R1 be 1 ohm, average value of R2 be 1 ohm. Let the standard deviation, okay, maybe I shouldn't be, I don't want to draw with touch. Okay, so let's say average value of R2 is 1 ohm, and then I'll use the keyboard here. And then we have the standard deviation of R1 is 1% or 0.01, and R2 is 1%, right? Because the mean is 1, the actual standard deviation will be just 1%, which is 0.01 into the mean value, which is 1, right? And then here you can see I have two columns. One is the expected value, which is based on the formula that I derived, and then one is the simulated value, right? So if you see wherever I have marked the expected value, I have actually written the formula. So the expected mean is R2 by R1 plus R2. So it is cell D3 divided by D2 plus D3. If you look at the standard deviation, then I have the formula that we derived, right, where I have said it is D7 is V out divided by R1 plus R2. That's the first term that you see. So D2 plus D3 in the cell here is R1 plus R2 into square root of H2 square, which is the standard deviation of R1 square, plus D2 by D3, which is R1 by R2 square, into H3 square, which is the standard deviation of R2 square. So whatever formula we derived is the simulate expected value is what I have entered under the expected value. And what I am trying to see here is I will run a simulation and I will check how close the expected value is with the simulated value. And again, I have done it, but I'd really encourage you guys to do this on your own, because I think it's very important for you guys to get comfortable with how to validate something quickly by running an experiment, by working with tools. It's a very core skill for anybody who wants to be an engineer. So let me walk you through what I have done here, right? So now if you see I showed you how the expected values were calculated. If you look at the simulated value, it is saying that the simulated value is actually coming from this sheet, right, the details sheet, and it is pointing to a specific cell. So let's go to the details sheet, and if you come to this sheet, you can see that under R1 I have generated 1000 values. These 1000 values represent the sort of, I bought 1000 resistors. This array of 1000 values is indicative of, suppose I had a standard deviation of 1%, what might the resistor values be? Now these resistor values, every lot will change, but the point is that the standard deviation itself, which is the square root of the sum of the square root of the sum of squares, will really not change, right? So now you can see that I have generated an array of 1000 numbers for R1. I have generated an array of 1000 numbers for R2, right? And then I say that, I know that the output is just R2 by R1 plus R2. So for each of these combinations of resistors, I am calculating the output voltage, right? The output voltage, if R1 is equal to R2, you expect the output voltage to be half, assuming input is 1. So you can see that the values are all around the half a volt output, right? Or R2 by R1 plus R2 is around half a volt, is around half. So then what I do is I say, now that I have generated an array of 1000 values for R2 by R1 plus R2, I can calculate its standard deviation. This is just a formula. So you can see that this is column G going from G2 to G1001, which is 1000 values, and this cell here is calculating the standard deviation for this array, right? And what I then do is I go back here, I say, okay, how close is my expected value, which is based on the formula that we just derived, how close is it to the simulated value? The simulated value is what is coming from the Excel sheet that we have made, right? So you can see that the numbers are very close, that if you have 1% variation in the resistors and a resistive divider which is nominally half, then the standard deviation will be about 0.7%. The benefit of this tool now is that we've built ourselves a nice tool to understand this system. So I can say, okay, what happens if R1, R2 is very high. Suppose my resistive divider is such that R2 by R1 plus R2 is practically 1. So R2 is much larger than R1. If R2 is much larger than R1, then what happens to the resistive ratio? Resistive ratio is R2 by R1 plus R2, but R2 is so much greater than R1 that it is practically 1. So you would expect that, or 0.999, you would expect then that the deviation will be very small because it is R2 divided by R2. So whatever variation is there in R2 doesn't matter, because when you take the ratio, or when you take R2 by R1 plus R2, that variation gets removed, right? And you would expect the standard deviation to come down as a percentage, and you can see that is happening, right? 0 is just because I am not taking enough decimal points. So if I keep increasing the decimal points, you will see that the number starts to show. But I have taken only 2 decimal points, that's why the number is showing up as 0, but it is actually 0.0014%, right? We will check the expected value here, that also is 0.0014%, right? So it is interesting to understand that, okay, although the standard deviation is also lower in this case, but you are now helped by the fact that you are dividing by a large number. So as a percentage, that standard deviation percentage is very small. Now suppose I flip it, right? Let's say I make R1 999 and I make R2 1, right? In this case, what happens? R2 by R1 plus R2 is actually just R2 by R1, right? At least when the resistive divider was a ratio of half, when the two resistors were equal, any variation was getting at least divided by or getting compensated by the other component. Whereas in this case, it is practically just R2 by R1, where you would think that, oh, now the standard deviation should be higher, because R2 can move in one direction, R1 can move in another direction, and there is no compensating effect. So as you would expect, here you can see that the standard deviation is, as a percentage, is much higher now. The standard deviation as an absolute number hasn't changed, but because the mean value is much lower, as a percentage the standard deviation is higher. So it's almost double of what it were when the resistors were equal, right? You can just go back to the detail sheet here for a second. You will see that it has automatically updated the resistor values, right? So it understands that, oh, okay, now the mean resistor is 999 ohms. It will generate the values accordingly, right? So it takes the mean value, it takes the standard deviation and calculates. So now what I can also do is I can say that, okay, I am interested in understanding, maybe I will keep it at 1 ohm, but I want to see what happens if, is it more sensitive to R1's variation, is it more sensitive to R2's variation. Suppose you want to do that, you can just say, okay, maybe I will make R1 vary more, and it will tell you what sort of standard deviation you can expect. Suppose I say, no, I will make R2 vary more. Actually from the formula you will see it really doesn't matter when the resistive divider is 1:1, right? But now you have a tool that you can play with, right? And I would very strongly encourage you to build your own. It's not very hard to build, but you can see that the minute you build a tool like this, you can go play with each value and see what is the implication of changing that value, and you can also see whether your understanding of the system matches with what the tool is predicting, right? Which is why here what I have done is, if you see columns D, E, I mean if you look at these few rows here, I am always contrasting expected versus simulated, and I try to see, okay, are they close enough? If these are random numbers and we are only taking a finite set, so it will not be exact, but you just want to be sure that it is very, very close. 0.71 and 0.69 are close. Now let's say I change the number a little bit, which I just run the result experiment again, right? Because every time I hit enter, it will regenerate the numbers. You can see that the simulated value is changing, right? So every time you are generating with a new set of 1000 numbers. I mean, you don't have to do just 1000, you can do with 10,000 numbers. If you do with 10,000 numbers, the amount of variation will come down. You do with a million numbers, the variation from run to run will come down even more. You do with 10 numbers, variation will be that much larger, right? But what I want you to take away from this session is the importance of balancing the analysis that you do with pen and paper with a tool that you can build to reinforce whatever your findings are from analysis, right? So simulation should always go hand in hand with analysis. The power of simulation is that you can quickly change variables and see whether how your output parameter is sensitive to each of these variables and whether it is consistent with your understanding.